Hi everybody. In this video we're going to talk about logarithmic functions. Logarithmic functions are the inverses of exponential functions. So if you think back to the first chapter where we did an overview of functions, we learned about inverse functions and that an inverse function will switch your domain and range, your input and your output. And so that's exactly what a logarithmic function does to an exponential function, or vice versa. They switch the input and the output, or they undo each other, okay? So here's a definition for you. If a is greater than 0 and b is greater than 0 and b does not equal 1, then y equals log base b of x. And that's exactly how you read a logarithm, okay? Log base b of x is how you read the logarithm. If and only if b to the y power is equal to x. Okay, so this is exponential form, b to the y equals x, and it converts to log base b of x equals y. Okay, so what is a logarithm more specifically? Well, if you look at this example, in exponential form, if it's base b raised to the p power equals n, that becomes log base b of n is equal to p. So essentially the logarithm equals the exponent. So what is a logarithm? It's an exponent. Okay? When you are converting from exponential form to logarithmic form, and here's an example that will probably make a little bit more sense. If you have 2 to the third power equals 8, that converts into log base 2 of 8 equals 3. You can kind of remember this as the drop and switch. Okay, when you're converting from exponential form to logarithmic form, you're going to write log, drop the base, and then switch your input and your output. So notice how the 3 and the 8 switch. Okay, let's look at some more examples, and I think you'll get the idea. Okay, so the first one is the same one that we just looked at. If we have 2 to the third power equals 8, that becomes log base 2 of 8 equals 3. All right, let's look at the next one. We have 2 to the negative 3 power equals 1 over 8. That becomes log base 2 of 1 over 8 equals negative 3. All right, then we have 5 to the r power equals s. That becomes log base 5 of s is equal to r. All right, then we have 10 to the 5th power equals 100,000. Now, this actually converts into what's called a common log. And we usually would just write it as log of 100,000 equals 5. When you don't see the base, it is understood to be a 10, and that's why we call it the common log, okay? All right, and then the last one, we have e to the x equals y. Remember, that's our natural exponential function. That converts into a natural logarithm. And the way we represent natural logarithm is actually with ln. It comes from the Latin form of the word, which was something like logarithmic naturalis. Okay, so it is natural log, but we use ln to represent natural log. So this would become natural log of y is equal to x. You don't have to write the base e because when you write the ln, it's understood that the base is e. Okay? All right, here's a little bit more about the common log and the natural log. Common log is base 10, so again, anytime you see log without the base, it's understood to be a 10. And then natural log, anytime you see ln, it's understood to be base e. Okay, next we're going to look at some basic properties of logarithms, and these really, come from the exponential form. And these are also valid for base 10 and base e. Okay, so for b greater than 0, and remember b cannot equal 1, and if x is greater than 0 and any real number y, then, okay, here's your first property. If you have log base b of 1, that will always equal 0, okay? Anytime you find the logarithm of 1, you know automatically that is 0, because when you raise a base to the 0 power, it always equals 1, okay? So because b to the 0 power equals 1, log base b of 1 equals 0. All right, the next property is log base b of b. So notice that these are the same. In that case, it's going to equal 1, because b to the first power equals itself, b, okay? All right, now the last two properties are using the fact that these are inverse functions, and they're going to undo each other. So if you have log base b of b to the y, that's just going to equal y. You can think of those as undoing each other. And then the last one, if you have b raised to the log base b of x, again, you have an exponential expression or a base raised to a logarithm with the same base. They're going to undo each other, and that's just going to equal x. Okay, so again, these are just highlighting the fact that these are inverse functions, and they're going to undo each other. Okay? All right, let's look at some examples. You want to be able to evaluate logarithms without using a calculator. So again, just you can think of the basic properties we just talked about, or just think of raising the base to an exponent, okay? So if you look at the first one, log base 3 of 3, well, that would equal 1, okay? Because 3 to the first power is equal to 3. All right, the next one, log base 6 of 36. Well, that would equal 2, because 6 squared equals 36. Remember, the logarithm is equal to the exponent. Okay, let's look at the next one. We have log base 3 of 1 over 27. Well, that actually equals negative 3, because 3 to the negative 3 would become 1 over 3 cubed, which would equal 1 over 27. Okay, the next one, we have 2 raised to the log base 2 of 37. Well, that's just going to equal 37. Again, because these are going to undo each other. Okay, next one, we have e raised to the natural log of pi. That's just going to equal pi, because again, these are going to undo each other. Okay, and then for our last example, we have log base 3 of 3 squared. Well, that's just going to equal 2, again, because these are going to undo each other. Okay, now we've talked about this in class already, but just as a reminder, we can convert fractional exponents to radicals. So remember, if you have x to the m over n power, that converts to the nth root of x to the m power. So notice that the denominator of the rational exponent becomes the index of the radical, meaning the root, and the numerator becomes the exponent of the radicand, which is the expression inside the radical. Okay, well, we can apply this to logarithms. So if you're trying to evaluate log base 9 of 3, you're trying to think 9 to what power equals 3? Well, if your base is 9 and you're trying to get a smaller value, that's a hint that you're looking for a fractional exponent, okay? Because if it's not fractional, like 9 to the first power is 9, 9 squared is 81, it's just going to get bigger and bigger. So think in terms of roots. Notice that the square root of 9 is equal to 3. So basically we're looking for the 1/2 power, okay? So this would equal 1/2. Because the 1/2 power converts into the square root of 9, which equals 3. Okay, next one, we have log base 125 of 5. We want to figure out what that equals. So again, the idea is 125 raised to what power equals 5? Well, we're looking for a fractional exponent here. So what we're looking for is 1/3, which converts into a cubed root. The cubed root of 125 is 5. Okay, so this equals 1/3. Okay, for our next one, we have log base 25 of 1/5. So, again, we're thinking 25 to what power equals 1/5? Well, the first thing I want you to notice is that we're looking for a fraction. So, in order to flip it, our exponent would have to be negative. So we know we're looking for a negative exponent, okay? And our base is 25, but then we want it to equal 5. So we're also looking for a root, and it would be square root. So basically we're looking for negative 1/2, okay? Because 25 to the negative 1/2 would become 1 over the square root of 25, which would equal 1/5. Okay? All right, and then the last one is log base 5 of negative 25. This actually has no solution, but again, if you think of it in terms of exponents, you'd be thinking 5 to what power equals negative 25? Well, raising a base to a power is not going to change the sign, okay? So this actually has no solution. You cannot find the logarithm of a negative number, and you'll understand that a little bit more when we start graphing logarithmic functions. The domain is actually x is greater than 0, but just know for right now you can only plug in values greater than 0 into a logarithm. Okay. All right, now we can also solve simple logarithmic and exponential equations. So to solve an exponential equation, you just want to convert it to a logarithm. And to solve a logarithmic equation, you just want to convert it to an exponential equation. So just convert between the two forms. All right, here's an example. We have log base 2 of x equals 5. So we're just going to convert that to exponential form. It would become 2 to the 5th power equals x. And then you can just evaluate 2 to the 5th power. It equals 32. Okay, let's look at the next one. Log base 2 of 16 equals x. That would become 2 to the x power equals 16. And then just think about that exponent. The exponent would have to be 4 here because 2 to the 4th power is equal to 16. Okay, then the next one, log base 3 of x equals 3. This would become 3 to the 3rd power equals x. And 3 to the 3rd power is 27. All right, and then our last one, log base 5 of 1 over 125 equals x. That would become 5 to the x power equals 1 over 125. We know we're looking for a negative exponent because that'll flip it. And then think 5 to what power equals 125? Well, that is 3. So we get x equals -3. Okay, so we're going to stop there. We'll definitely do some more practice in class with this. So thank you for watching. Have a good night.